Okay, hi everyone. All right, today we are going to have a working session talking about potential experimental implications of our models. And the thing, we last did this actually a very long time ago now. It was in beginning of September of last year. We were looking at this and I've been meaning to get back to it, but there keep on being these other projects that are more theoretical in nature in many cases that have gotten in the way. One of the things that's happened recently is Jonathan just finished his big paper about using our models to do practical numerical relativity and compute things like black hole mergers and so on. And so I was hoping that we could see how to use what Jonathan has figured out how to compute to actually talk about some potentially observable consequences of our models. So maybe we could start off, maybe Jonathan could give a quick tour of some highlights of some of the cool pictures from his paper and things.
Okay, so I could give or I can give a sort of brief high-level summary of what's going on. So if I share my screen, okay, so here's the paper on arXiv. This should be the PDF that is currently loading. It's a sort of 40 megabyte-ish paper because of the pictures, so it takes a minute to load.
Oh, did arXiv finally post it?
Yes, yeah.
You weren't going to crash their servers? Okay.
It's a very amusing thing. Okay, sorry, slight diversion. It's a very amusing thing. arXiv clearly have difficulty classifying the papers that come from the physics project. They can't decide whether they should be, general relativity, quantum cosmology, high energy physics, discrete mathematics.
This is good. This is good. This is a sign of a new paradigm. That's.
Every time I pick a category, it seems to get reclassified.
Okay.
But anyway, so yes. Anyway, so basic context is. Okay, so we have known for a while now that there exist classes of these Wolfram model rules which satisfy the Einstein field equations in the continuum limit, so long as they satisfy certain axioms, specifically causal invariance, sort of asymptotic dimension preservation, and ergodicity, as we might define later. But one of the things we wanted to do was to see that explicitly, to produce a space-time that was produced by a solution to the Einstein field equations, then produce a space-time yielded by one of our Wolfram model systems and show that they were actually the same. So this paper was, in a sense, an attempt to do that. So the main thing that happened was I developed a numerical relativity code based on this thing called the CC-Z4 formulation, the conformally covariant Z4 formulation.
What does the Z4 stand for? What does that mean?
So Z or Z is a relativistic four-vector thing that you introduce, which is this Z mu thing here, which essentially takes the role of the ADM constraints in the standard ADM decomposition. So in ADM and in formulations that are based on ADM, like BSSN and other things like that, you have these four constraints: the three linear momentum constraints and the one Hamiltonian constraint. The Z4 formulation differs only in the sense that it replaces them all with a single constraint for one four vector, which is this thing called Z for reasons that I don't know historically.
What is the constraint, though? I mean, so the thing you previously described sounds like it's an energy momentum vector. The thing you were describing, energy and Hamiltonian and three momenta, that seems like a momentum four vector.
It's related to the momentum. It isn't a momentum four vector, but it's related to the momentum four vector. Yeah.
Okay.
I mean, the momentum four vector is just p mu, which is not quite the same thing.
Right.
But yeah, they place constraints on each other. Essentially, what's happening is, okay, so when you take your space-time, you foliate it into these space-like hypersurfaces, and to pick your gauge at every point, for each geodesic normal observer, you are having to select a lapse and a shift that tell you how to get from this hypersurface to the neighboring hypersurface.
Right.
When you do that conversion, so you get when you convert to the Hamiltonian formulation, you have the six components of the spatial metric tensor on the hypersurface. They convert into six constraints on the extrinsic curvature of hypersurfaces in the dynamical theory. Then you have the lapse function that converts into a Hamiltonian constraint in the dynamical theory, and then the three components of the shift vector convert into a momentum constraint in the dynamical version of the theory. And all that's happening with the Z4 formulation is you're packaging all of those up into a single thing, which is the Z variable. And if you change some details of how the projections are taken and how the constraints are enforced, it reduces to the standard BSSN formulation. So
is that Jose I see mentioned up in the...
Yes, I was going to bring that up, that we have one of the sort of the promoters of the CCZ4 formulation on this call.
Right. I did work on that. Yeah. I did.
Okay, it's but and so how all this stuff works outside of 4 dimensions, who knows? Or have you figured that out now?
Oh, I mean, there's no obstruction to doing this in higher dimensions. You just you end up with a shift vector that has more parameters, so you get additional momentum constraints. But
so in the hypergraph situation, where you don't have any particular dimensions at all, can you formulate these things there?
Yes, but it requires having a generalized picture of what a vector is, which is fine because we have that. It's a GD6, so that's all safe. But when you try and convert it back into this formalism, you're left with a situation where your Z vector doesn't necessarily have an integer number of entries.
Okay, fine. And it corresponds to some geodesic, is that right? It corresponds to a geodesic that is somehow defining these space-like hypersurfaces, is that right?
Well, actually, I think I can show if I skip ahead ridiculously, I can show somewhere something which might help explain. So these pictures, which are taken from your technical introduction, actually give you a pretty good illustration of what's going on. So suppose we have this event here on this hypersurface up there, and we have this event here on this hypersurface, which is the next sort of neighboring thing.
Yep.
Right. So what you're basically asking is the alpha parameter is telling you how many causal edges do I have to traverse to get from this event to that event. And the beta parameter is saying, okay, this event gets applied at some position in the hypergraph, and this event
the lapse. The alpha is the lapse function of the ADM formalism.
That is correct. Yes. And the beta is telling you, so this event gets applied at one position in the hypergraph, this event gets applied at a different position of this hypergraph. And so then the question is, if you ignore all the other events, you just consider those 2 regions of the hypergraph that are just given by 2 subgraphs. The beta parameter is essentially telling you what are the paths needed to map from one of those subgraphs to the other subgraph.
Or in some sense, the spatial distance, in some definition of spatial distance, right?
Well, so a projection of beta I onto the hypersurface would be exactly the average spatial distance between those 2 events. Yeah.
So I could have formulated my faster than light discussion in terms of the beta parameter, in terms of this beta parameter that you're describing.
Yes.
Might be an interesting thing for somebody to do.
Right. Well, I mean, yeah. So faster than light occurs. FTL occurs exactly when the angle of the shift vector exceeds the lapse function in some appropriate units.
Right. Okay.
Anyway, that's what's going on. So okay. Anyway, so I'm going to try not to get too bogged down into the formalism, but the basic idea is we start from the CCZ4 formulation, which is this standard way of doing relatively standard way of doing numerical relativity, that has these nice properties. So conformal. It's invariant under conformal transformations because the variables you're evolving are not physical variables like the spatial metric tensor or the extrinsic curvature tensor, but they are those variables modded out by a conformal scaling factor, which means that the whole formulation is invariant under conformal transformations, which is good for us because we believe our causal graphs are also invariant under conformal transformations. And it's generally covariant. Actually, okay. Slight subtlety is we end up breaking the covariance slightly for the black hole simulations, but that doesn't really matter. But the important thing is that it's in its natural formulation, it's covariant, which is also good for us because our causal graphs for causal invariant systems are also sort of generally covariant. So that's why I picked this particular way of formulating the equations. Okay, so then the basic idea was as follows. So a standard numerical general relativity code will evolve one space-like hypersurface to the next space-like hypersurface, but where the space-like hypersurfaces have some fairly rigid coordinate grid structure, right? So normally how it works is you have maybe a single curvilinear coordinate grid or maybe a set of overlapping curvilinear coordinate grids. And if you're very fancy, you might have some adaptive mesh refinement where the individual coordinate grid cells get refined recursively, but they're only ever refined in a way that sort of preserves the same structure. So when you refine a patch of cells, you're still refining with respect to a curvilinear coordinate grid system. So in other words, in a standard numerical relativity code, the topology of the grid structure doesn't really change in any serious way.
Yep.
But of course, with our hypergraphs, the topology is changing all the time. So the obvious question was, could we set up a numerical relativity code where the grid structure had a dynamic topology? Because that's essentially what we would need in order to make comparisons against full Wolfram model evolution.
Yep.
So that's what is going on here. So first challenge is, okay, we don't have a coordinate grid structure like this. Instead, we have some more general hypergraph structure. So first challenge is, how do you set up something like a finite difference stencil? Then, okay, we have a way of essentially setting up, because we know how to take inner products of geodesics, and because geodesics are like the analog of vectors, we can set up a local coordinate basis around each neighborhood in the hypergraph, and you can use that local coordinate basis to set up these finite difference stencils. We use an interpolation scheme in order to assign values to the cells, blah, 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 blah. Okay, so then this is the information about how we do the mesh refinement. So we take the standard or a standard adaptive mesh refinement algorithm that's due to Berger and Colella, and we generalize it to the case of these hypergraph systems. So what we do is we say, okay, so for these physical simulations, we're refining on the basis of conformal curvature. So we test whether projections of the conformal curvature tensor at a particular vertex exceed some value. And if they do, then we mark that vertex for refinement. And when we mark it for refinement, what that means is, so like here, you can see a bunch of colored vertices that have been marked for refinement. Like this red vertex here has been converted into this patch of 4 red vertices there. So all we're doing is we're taking one vertex and we're splitting up into 4 vertices in such a way that the newly introduced subgraph preserves the neighborhood structure of the vertex that was refined, right? That's the idea.
Yeah, I think one of the coolest things of what you're ending up doing is that in our models, they refine themselves.
Right. So okay, yes. So
our models and biology, probably the two cases that refine themselves. That is, in a biological system, probably if the thing is deformed, then there'll be cellular, the cells will divide in those places or whatever, and there'll be more cells. That's probably these are, and in fact, there's probably something could even be done with that correspondence, because now that I think about it, there were some people who were studying plant growth who we should show this to, now that I think about it. There were some people, because they exactly need exactly this type of thing, and they have a hard time with it. And they have, I'm going to make myself a note to make sure we mention this to the plant growth people. They may be a little bit scared by seeing all this relativistic stuff, but I think
we can strip that out.
I'm
excited to see numerical embryology.
Well, yes, that people try to do that, and it's I mean, actually, plants are the thing. I mean, animals are squidgy. Plants have cellulose cell walls, which means that they tend to grow and add things and don't tend to, do the same kind of subdivision type stuff. They subdivide only in particular places. Anyway, let's not talk about plant biology. We're off on a different topic here.
So what I was going to say was that so obviously we have ways of extracting curvature information purely from the topology of the hypergraph. And that's normally how we think about things in the context of the physics project. What we're doing here is the reverse of that. We're using a priori curvature information that we know from having an actual conformal curvature tensor to modify the topology of the hypergraph so as to match that value. And then what we're going to do at the end is show that actually you didn't need the conformal curvature tensor anyway. You could have got all the information you wanted just from the topology. But anyway, that's what's to come. So, so in effect, what we're doing here is we're introducing artificial curvature into the hypergraph in accordance with the conformal curvature tensor. Okay, we have to slightly modify how the fluxes are then calculated, because now we've got sort of coarse subgraphs that might be abutting fine subgraphs, and then in that case, in order for the current condition to be satisfied, essentially what you have to do is you evolve the coarse subgraph by one time step, and then you evolve the fine subgraphs that are abutting it by as many time steps as they need to in order to kind of catch up, and you have this whole recursive subcycling procedure that kind of takes care of that. Anyway, that's
all right. Complicated numerical analysis. Let's get the goal here is to get to talking about.
And we're doing a less structured version of ordinary mesh refinement, where here, if we compute a projection of a curvature tensor along an edge and it exceeds some value, then we just subdivide that edge. And likewise, we have a coarsening procedure where if the conformal curvature tensor projection drops below a certain threshold across two adjacent hyperedges, then we merge them together and we get rid of the intermediate vertex. So at every step, the hypergraph is being progressively refined in regions with high curvature and progressively coarsened in regions with low curvature. That's the sort of idea. Okay, so now let's do some actual experiments. Okay, so here, let's we're setting up, so these are with different resolutions. This is 100, 200, and 400 vertices respectively. So here we're setting up initial conditions for a Schwarzschild solution, just an ordinary static Schwarzschild solution. And then we're evolving it for a certain number of time steps. We're evolving it for in dimensionless, in geometric units. We're evolving it for a time that's 1,000 times the mass of the black hole. And we show that we actually get sort of stable evolution. And so here are the causal graphs that we get out, which are showing us effectively the conformal structure of the solution. In effect, to build these causal graphs, all I'm doing is I'm tracing the characteristic line. So I'm looking at, when I compute the fluxes between neighboring hypersurfaces, where is the information flowing in the hypergraph? And I'm using that to construct.
So if I think about a light cone superimposed on that causal graph,
yeah,
what this is showing me, so a light cone would normally go from a node in the causal graph, and it will just go to the ball of nodes or the cone of nodes that can be reached. How do I see the tipping of light cones here? Well,
the tipping of light cones has already been seen, because in a sense, for most of this causal graph, you're actually inside the event horizon. So what you're seeing here is, once you're in this region, all of the light cones intersect this point down here, right?
Okay.
And so what that is, sorry.
That's the space-like singularity at the center of the black hole. Is that right?
Right. So what that is essentially telling you is, once you're in this region of the causal graph, there is all points have a common future, and the common future is the singularity.
Where's the event horizon?
So it's somewhere out. It would be somewhere out here. So if you were to, I've excised everything that's outside because you don't really care about it for the causal structure. But if you evolve the whole thing, this region here and this region here would evolve in their own merry way.
So do you think if you were to do this, if you were to use your code basically to evolve the space-time plus the black hole, that you would see kind of a rip in the causal graph there?
Right, exactly. Yeah, you would see a sort of a pocket of the causal graph that things went into but things didn't come out of, which is sort of
right. Which is then. But do you think you would see separation of the causal graph, or do you think you would just see causal edges? You'd see causal edges that lead you in those two different directions, and you can't then cross the event horizon.
Right. It wouldn't separate entirely, because you can always get in, you just can't get out.
Right.
So if you had background space-time here, that's partly why I didn't render the background space-time, because it would be too kind of confusing. But what you would see is edges pointing into this conical region, but there'd be nothing coming out.
So what can we learn about what happens to stuff inside the event horizon from these pictures?
I don't know. I'm not sure that anyone, Jose could maybe answer this better than I can, but I'm not sure how seriously people take validity of the Schwarzschild solution inside.
They don't know what's going on.
Right. So given that this is produced by a Schwarzschild solution, it's unclear what
later on, you're going to do this without the scaffolding of that, and then it's going to get more interesting.
Yeah. The interesting thing is, actually, when you do it without the scaffolding, it looks very similar to the Schwarzschild solution, which is perhaps telling you something. But anyway, so this is a boring table, but it's an important table, because what it's showing, we know the analytical value of the Hamiltonian constraint, because it's a static, constant mass black hole. So we know the Hamiltonian constraint should remain steady. And similarly, we know the linear and angular momentum constraints should remain stable. And so one important check is to make sure that as you evolve it over arbitrarily long timescales, that regardless of the resolution, that they all converge to the right answer, and that they all remain stable, which indeed they do, and they converge with roughly fourth order accuracy, which is unsurprising because it's based on a fourth order Runge-Kutta finite difference scheme. And
how accurately does the dimension stay constant? Do you know?
So that is a good question. I looked at it. I didn't include it in the paper. It looked as though the violations of the dimension. Okay, so in effect, in addition to the ADM constraints, we also have our dimension constraint that doesn't normally exist in relativity. And from what I could see, the violations of the dimension constraint didn't seem to exceed the violations of the Hamiltonian constraint, which I guess is kind of unsurprising. But
you see, this is very important, because we really care about dimension fluctuations. In the real situation, we're really going to care about dimension fluctuations. Right. So in the real situation, this is always what people doing numerical analysis get afraid of, right? Is that in the end, this isn't numerical analysis. In the end, this is actual analysis of a potentially fundamental underlying model. Not yet, but later on, that's what you're doing. And so then these things where you're sort of saying, oh, no, don't look there because it's a violation of the numerical analysis. Those are real phenomena. And that's actually what in a sense, what I was hoping to concentrate on today was essentially those places where if you were doing numerical analysis, you would say the numerical analysis breaks down because that is precisely what we want to see in terms of understanding discreteness of spacetime and the effects of discreteness of spacetime and so on.
No, I completely agree, but I think it's important as the first step not to go there, right?
I agree. So
for the sensible cases that are well known, we want to show that what we have is robust, and then we can, once we have a robust thing that tells us about the stuff we know about, we can take seriously the predictions it makes about the stuff we don't know about.
Fair enough. Okay, keep going.
Anyway, yeah. So then these pictures are ones that are taken. So these are just the same hypergraph pictures here, but where I've coordinatized the thing. So one thing we can do that we can't do with ordinary Wolfram model evolution is because these are produced by a solution to a PDE system, we know the coordinate structure. So we know the spatial coordinates of all these vertices, and we also know the values of the conformal curvature, the Schwarzschild conformal curvature. So what I've done here is I've just taken a projection onto along the z-axis of one of these space-like hypersurfaces, the initial space-like hypersurface, and then I've assigned the z-coordinates in accordance with the local conformal curvature. So regions down here where you see the thing is red, those are high conformal curvature. Regions up here which are blue, they're low conformal curvature. And this is off.
How many points are there across the black hole?
How many points did you say?
Yeah. How many points?
So on the right here, that's 400 vertices. Okay.
And how does that compare when people do numerical relativity for black hole mergers and so on? How does that compare with what people are doing in practice there right now?
This is disgustingly low resolution in comparison.
What do people actually use really?
So like in the kinds of simulations I've been doing recently, not in the context of the physics project, like 1,000 by 1,000 as 1,000 by 1,000 by 1,000 as a base grid resolution is reasonably common for relativistic binary and spirals, that kind of thing.
So you and here you said 400 altogether or 400 across?
400 altogether.
Okay, so it's the cube root of that, or it's the fourth root of that.
Cube root.
Okay.
So very low resolution by comparison.
And how much? I mean, in the standard case, where you have, I have to work out what the cube root of let's see, cube root of okay, so that's 8 vertices across the black hole, so to speak.
Right.
So how does in the usual calculations of things like black hole mergers, how does it degrade typically as you reduce the number of vertices? And what goes wrong first?
Okay, that's an interesting question. I mean, I don't think anything goes dramatically wrong. You just get progressively more numerical diffusion until, for instance, you might get so much numerical diffusion you could no longer distinguish, 2 sides of the event horizon or something. And that's the point at which I guess your solution becomes completely worthless.
But numerical diffusion means what? It means that the curvature is smeared out over some region, is that right?
It means you have too large a curvature change from one grid cell to the neighboring grid cell.
And so, is it, and so you can't trust it?
Well,
because you're approximating the derivative by too big a jump.
Right, you're linearizing a function that's on, as the scale at which you're looking at the function gets larger, a linearization approximation becomes less and less reasonable. And so eventually you're coarse graining out so much microscopic detail of the function by linearizing it that it's no longer it's no longer a viable solution to anything.
And another important thing here is that if I understand correctly, these 400 points are very close to the black hole, while in standard simulations, one typically wants to have an area around the black holes or the binary black hole, because you are interested in observing, say, gravitational radiation observed from some distance.
I see. I see. So how far out do you usually go in those simulations? I mean, in an actual merger, are you going to, many 1,000 times the black hole radius, or are you going to like 5 times the black hole radius?
200 or 300 seems to be quite common in my Sorry, Jose.
Right. Yeah, exactly. So it's not very large because you want to still resolve the black holes, and but it has to be some distance. I mean,
Okay.
once you are far enough, you can use perturbation theory or things like that to predict what would happen farther away.
Fair enough.
This is also the reason why adaptive mesh refinement is so important, because some regions need the
Right,
resolution.
because there's actually a black hole somewhere, and most places space is just kind of flat.
Right.
Okay.
Anyway, so yeah, so that's the boring static black hole case. This is the slightly more interesting, but still not particularly interesting Kerr black hole, rotating case. So these are, so A is angular momentum is the mass normalized value of the angular momentum parameter. So here it is at 0.3. So you can see there's a slight disconnect. So for a Kerr black hole, you have an interior event horizon, you have an exterior event horizon, and you have an ergosphere that sort of separates them. And so here you start to see you might start to see separation of the interior and the exterior event horizons, and you see the thing is becoming slightly sort of squashed. At 0.6, it becomes slightly more squashed, and you see more detailed separation.
Wait a minute. These are the coordinates that you're getting from, because this came from an actual metric.
No. So these are uncoordinatized. This is just default graph. This is spring electrical embedding.
I see. So there's intrinsic. Wait a minute.
These are the coordinatized variants.
I see. So there's of the Kerr black hole.
Yes.
Okay.
So here you can see that this is at 0.9. You
what
see
the
very
heck
strong.
Does it do?
Sorry.
What is it doing? It's breaking up.
Well, so at 0.9 you can see there's strong separation of the interior horizon from the exterior horizon, and it looks tipped. It's not actually tipped. That's just how the 3D graph rendering shows it. It appears tipped because it's being stretched, and you can see the stretching perhaps better in the uncoordinatized pictures. So here it is at 0.9, and here it is at extreme, sort of almost supercritical velocities.
What happens if you go beyond criticality?
Beyond criticality, it disconnects entirely. You get a disconnected subgraph.
So wait a minute. So dynamically it disconnects. Is that right?
Yeah.
So what's the disconnection time?
What you mean in terms of simulation time?
Yeah, I mean in terms of scale coordinates. How long does it take a mass M black hole to have that is spinning at supercritical angular momentum to have? I mean, does it disconnect immediately, or does it take?
The initial, strictly speaking, the initial conditions. If you did pre-processing on the hypergraph that refined the thing perfectly, according to the conformal curvature, the initial conditions would start off disconnected. So it's an instantaneous effect. I don't think there's a disconnection time.
Okay, and the disconnection though. Let's see. Okay, all right, and you're going to show in the causal graph what happens.
Right. It's kind of hard to see it's hard to say what happens in the causal graph, other than the fact that the space-like singularity region gets sort of smaller. I mean, the interior region of the causal cone before you hit the space-like singularity gets longer at higher angular
What's
momentum.
the signature of the ergosphere in the causal graph?
I can't point to one offhand.
What is the normal picture of the ergosphere in terms of Penrose diagrams and all those kinds of things? I mean, doesn't it have a very definite? I remember these pictures of. Isn't there a very definite sort of causal character to the ergosphere?
Yes, yeah, but I mean, we're not. But these aren't. Although they're representing the same thing as Penrose diagrams, but they're not they're not laid out as Penrose diagrams, so I can't immediately point to the features.
Could we lay them out as Penrose diagrams?
With enough reverse engineering of the events, we could, yeah. It's possible.
Because we know where the events are in space-time in your setup. That would be kind of an interesting thing to do, I think.
I agree. Yeah, it's worth doing.
In the Penrose diagram, this reminds me, did we forget again? Sorry, I'm just changing something here. Just a second. No, anyway, but in the Penrose, I mean, let's guess how the ergosphere will show up in this causal graph. Can we do that? So what would happen? I mean, so in the end, a particle.
Well, the key feature of the ergosphere region causally is that the G whatever it is, the GTT component, the double time component of the metric tensor is always positive if you have a minus plus 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 metric convention. So in other words, you only in the static non-rotating frame, you only have space-like distances. All of the time-like and light-like rays must co-rotate with the black hole. So what you would need to, the signature would be, okay, what you really want to do, I think, and we have ways of doing this now, but I just haven't done the visualization. What you would really want to do is show the local relativistic angular momentum at each point, and then show that for all of the anti-chains, you could, no, not for all of them, that you can have anti-chains that have zero angular momentum, but everything where there's causal connection has non-zero angular momentum. And then that region with that property would then be the ergosphere, I think.
So it's like infinite frame dragging of some kind.
Yeah, to the point where frame dragging becomes unavoidable, if you like.
And how would we see that here? Okay, fair enough. Okay, well, keep going.
I mean, so the point is we have a way of extracting purely, well, either in this case we can cheat because we already know what the angular momentum tensor is, but even in the purely Wolfram model case, we can extract an angular momentum tensor because it's, I mean, we know what the angular momentum construction looks like. It's just you're taking net flux of causal edges round, across a hypersurface as you rotate that hypersurface. So we could absolutely color these vertices by their angular momentum, and then show that there's a region in which all of the time-like paths have non-zero angular momentum, and then that would presumably give us a way of recognizing.
Okay, all the time-like paths. So wait a minute, but each node gets angular momentum. Is that correct?
Yes.
Relative to what axis?
Well, the axis of the black hole.
Okay. But it should get an angular momentum vector, yes?
Right.
So
the point is that in the space-like directions, you're free to have zero angular momentum. But in any time-like or light-like direction, you have to have non-zero angular momentum if you're inside the ergosphere.
Mm-hmm.
That's as far as I know, I think that's the most direct way of seeing that in one of these causal pictures. I don't know, Jose, do you have other comments?
No. I think you're right. So corrotation is the key thing for the ergosphere.
Okay. Let's keep going here, and then I'm.
Right. We want to get onto the experimental prediction stuff. Okay, this is a fun test. I mean, it's completely unphysical as far as we know, but this is a maximally extended Schwarzschild solution. So if you take, there's an extended version of the Schwarzschild coordinates, which are these so-called Kruskal-Sekares coordinates, and they allow you to construct a maximally extended version of the Schwarzschild solution where you extend beyond the space-like singularity, and you end up with this sort of two-sheet, like a two-sheet hyperboloidal kind of solution, where you essentially have an exterior solution, an interior black hole solution, an interior white hole solution, which is like the time reversed version of the interior black hole solution, and you have some exterior parallel universe solution, which is which is outside the event horizon of the white hole. And so there's a theorem that essentially says that is the maximal analytic extension that you can make of the original Schwarzschild solution. So you get an example of a non-traversable wormhole or an Einstein-Rosen bridge metric. So here we're simulating that. And as was shown by Wheeler and some other people, as I say, this particular example of a wormhole solution is non-traversable. And the reason it's non-traversable is because the neck of it will stretch and essentially pinch off faster than anything could in principle get through it. So if you wanted to try and go from the black hole region to the white hole region, the neck would grow faster than you could fall through it. And actually we can see that here. So you can see the neck is actually growing and progressively pinching off. This is the causal structure here. So you can see this is the this is up here is the ordinary black hole solution, and then down here is the time reversed version of it, which is the white hole solution.
But you're essentially, I mean, if this was computer animation, you would be doing some kind of rigging thing, as in you've already got the framework, the skeleton of this thing is already defined by your external, by the way that you are setting up the original space-time nodes. Is that correct?
Yes.
I mean, this didn't dynamically evolve this way.
Well, it dynamically evolved. So this is the initial rigging, if you like, this picture here. And then, so these subsequent pictures are the dynamic evolution where you see the neck stretching out.
So, I mean, for example, if you look at those causal graphs, can you see this phenomenon of not being able to fall through the neck?
Well, you can see it in the sense that anyone who tried to get through would be crushed into this space-like singularity on either side.
And how many is that yellow thing in the middle? Is that lots of dots?
Yes. I mean, in principle, that would be an infinite number of dots, but it's been compressed.
I see. So in other words, that the fact that is elongating, and each one of those dots takes one elementary time to get from one dot to the next.
Right.
And so what you're saying is,
yeah, in the true extended version, it would, there's finite time to get to this point, then there's infinite time, and then there's that solution there.
What is the relationship? Just a general knowledge question. I mean, I remember from long ago, this the periodicity of the Schwarzschild solution in imaginary time. If am I misremembering that? I think it's periodic in imaginary time, isn't it?
I think that's right. Yeah.
What is the relationship of that to what you're seeing here? Is that the hyperboloid meets? I mean, is that just a transformation from hyperboloid to sphere or something?
I would suspect so. I would suspect what you're seeing here in the Kruskal-Sekharez solution is you're seeing one period of that oscillation, or half a period maybe of that oscillation. But
so I'm wondering about the imaginary time case. I mean, the question, imaginary time may have nothing to do with our models. As in, it may just be a mathematical artifact that happens to be used in standard, quantum field theory, and it's just irrelevant to our models. But it will be interesting to know whether there's some trace of things that happen in imaginary time. Could we imagine an imaginary time analog of what you're doing here?
Right. Actually, I'm gonna pass it on to Jose because he knows these things better. I mean, is there a relationship between the Kruskal-Sekharez extension and periodicity of Schwarzschild?
If there is, I don't know about it.
Okay.
I was not. No, I don't know about it. Sorry.
Okay. I mean, it's probably maybe it's only quantum field theory people who use the imaginary time case.
Yeah, I've heard about it, but I don't know anything really substantive about it.
Okay. All right.
Anyway, yeah, this is nice because it's just showing that you can still simulate topologically non-trivial spacetimes and get the right answer.
It was popular back in the day because it sort of corresponded to Hawking temperatures and things, because it corresponded, that imaginary time periodicity was analogous to the temperature versus quantum effects story in imaginary time. Okay.
Well, actually, I have a slight Hawking related diversion about this particular solution, so which relates to actually the colloquium talk we had last week from Mark van Ramsdonk, which I thought was a really interesting talk, which is about a way that we might be able to connect this solution in particular to some of the work that's currently being done at sort of the frontiers of ADS-CFT correspondence in quantum gravity. Because so one of the general classes of predictions that one can make on the basis of holography and ADS-CFT is this prediction that when you have an Einstein so there's this whole idea, the ER equals EPR conjecture, right? That you can think of entangled particles as being connected by a wormhole solution of exactly this type, an Einstein-Rosen bridge solution. And a quantitative way you can formulate that statement is you could say, if I consider the Einstein-Rosen bridge to really be like a black hole and a white hole or something that are entangled, I can compute an entanglement entropy, a space-time entanglement entropy with that associated with that configuration. And I can also compute a sort of ordinary Bekenstein-Hawking entropy that's associated with the black hole. And the one way you can formulate the ER equals EPR conjecture is as the statement that those two entropies are actually the same, that they converge to the same answer. And one of the exciting things is that one of the projects I'm currently trying to kind of encourage people to work on, that I've already started working on it, I'm trying to encourage others to work on it as well, which is defining essentially quantum scalar fields over these hypergraphs, gives us a way of computing a space-time entanglement entropy and a Bekenstein-Hawking entropy associated with these space-time configurations, which means that by examining this solution in particular, we may have a way of numerically validating or falsifying at least the ER equals EPR conjecture within this model, if not more general statements about AdS-CFT. Anyway,
hey, walk through that a little bit more carefully for a second. I mean, so define, let's see. I mean, to put a scalar field on it is somewhat like what you've been doing. I mean, what you've been doing here is you set down these points in space-time, but when you say put a scalar field on them, you mean assign values to those points, yes, that correspond to a scalar field.
Right. So think about what we've already been doing with just the pure numerical relativity stuff, right? We've in a sense we've defined a tensor field across the hypergraph, right? The Riemann curvature tensor field.
Yeah.
And then we're refining the hypergraph topology on the basis of that tensor field, and then we're saying actually we could recover the tensor field information just from the topology, so we didn't need the tensor field in the first place, right? That's the sleight of hand trick that's being done. So we could do the same thing. In addition to a tensor field, we could have a scalar field that lies on top of it that's coupled to the underlying tensor field. And we can do the same. And that scalar field can also be part of the refinement criterion. And then we should be able to do exactly the same thing.
It's a little bit less clear to me that will work, because I mean, we know we can derive the Einstein equations from the underlying model. We don't know whether we can derive the equations of motion for a scalar field from the underlying model.
Well, we know we can derive the vacuum Einstein equations, but we also know we can derive the non-vacuum Einstein equations. So all the scalar field is doing is it's giving you the simplest non-vacuum solution.
Right.
Right.
So wait a minute. So what you claim is that by somehow injecting causal edges to lead to energy momentum, that.
Right. The only difference between the construction we already have here just for the curvature and the energy momentum, the simplest energy momentum construction, which is just a single scalar field, a massive scalar field, minimally coupled, is that reconstructing the information about the massive scalar field requires some global information, which you don't normally the construction is completely local. But basically what you need to do is you take your hypergraph, you extract all the curvature information, and then you want to say, accounting for the curvature, are there regions where there's higher than average causal edge density? And if you take the average causal edge density to be essentially the vacuum, then the regions where there's higher than average causal edge density are the regions where the scalar field is positive, and so on. And it's a slightly hand-wavy way of saying it, but that's the basic idea.
Okay, but so wait a minute. The curvature, your claim is that there will be places when you take the space-like hypersurfaces, you'll be able to have certain curvature that you get there. And what you're effectively saying is, are there regions where there is higher activity, that is higher number of causal edges, than is necessary to maintain that spatial structure, that curvature structure?
Exactly, yeah.
Right? So, in other words, the presence of matter and all of us is excessive activity, so to speak, that goes beyond what's necessary to maintain the structure of space. So the question is, can you in your models numerically figure out what is the minimal amount of activity necessary to maintain that structure of space? How would you do that? How would you figure that out?
Well, I mean, so one cheaty way we could do it is just by evolving the thing without a scalar field, and then and assessing what's the characteristic activity required to maintain that space. We have some conformally flat space-time that's vacuum, and we evolve it, and we just compute the activity, the causal activity needed to maintain that structure, and then we evolve the thing with a scalar field, and we just use that original reading as a baseline, and anything that goes above that we interpret as matter field.
Well, yeah, right. Or alternatively, just say, let's inject activity, even when the activity is just spinning around doing nothing,
right,
and not affecting. That will give you energy momentum, although that energy momentum will probably have little dynamics. If all you're doing is just making things spin around randomly, that's more like cosmological constant. It's not going to have any dynamics.
Right. But one of the things I'm currently working on with a few people, Sam Whittington and Greg Kaplanek and others, is trying to basically construct what's the minimal massive scalar field Green's function that you would need to define in order to have, a scalar field with non-trivial dynamics in one of these models. And I have a candidate at least. There's a general ansatz, and I managed to find a candidate that seems plausible, that fits the ansatz.
Right, okay, so we got the scalar field. This gives us some way of computing, so you were going to explain, the entanglement entropy has to be a different story having to do with branchial graphs and things. Yes,
right. Well, actually, both the Bekenstein-Hawking entropy and the entanglement entropy are associated with branchial graphs in an indirect way. So this is a slightly hand-wavy statement because we haven't done the maths yet. But here's my basic idea. So once you have a classical scalar field on one of these hypergraphs, which by the way I've managed to produce, and it does indeed appear to obey a discrete analog of the Klein-Gordon equation and so on. Then the question is, what happens if you make it quantum mechanical? And the way you make something quantum mechanical in our model is, of course, you just evolve it as a multi-way system. So then what you end up with is a multi-way system where the branchial graphs are now giving you the space of possible solutions, the space of possible mode solutions to the discrete Klein-Gordon equation. Then, as I know we've discussed this before, my basic idea is we partition the branchial graphs into two subgraphs that correspond to the positive and negative frequency classes of the modes. And although I know this is not normally how it's thought of in regular quantum field theory, at least the way it's thought about in axiomatic quantum field theory is that you then define the vacuum state relative to those positive and negative frequency classes. From that and from the Pauli-Jordan function we can also construct a Pauli-Jordan operator because we know the advanced and retarded Green's functions for the classical case. So then from all of that information, we can construct a discrete Whiteman function. And as long as we assume the quantum field theory is non-interacting and that it has a Gaussian state, we know that that Whiteman function is sufficient to completely determine the dynamics of that quantum field theory in curved spacetime. So then we have essentially a numerical theory of quantum field theory in curved spacetime, which is quite cool. And from that, from information about the Whiteman function and the Pauli-Jordan function and so on, we should then be able to compute spacetime entanglement entropies and Bekenstein-Hawking entropies, essentially just using the ordinary approaches that are used in usual quantum field theory in curved spacetime.
All right, so let's run through what you're claiming here. So first of all, in a particular non-branchial version of all this stuff, you would essentially have a classical field equation for the scalar field.
Yes.
Okay, so in our models, what it means to quantize, it's very nice that we actually have that's been such an obscure word for 100 years. In our models, what it means is you follow all the multi-way branches. That's it. Instead of just saying you follow one multi-way branch, you follow all of them. That's what it means to quantize, so to speak.
Right.
So now you're saying, and then that in general has many different things that can happen. So now you're trying to say, and I don't know how important that is, that you are trying to look at the energy spectrum of those different multi-way possibilities, and you're making a claim about there being positive and negative energy modes.
Yep.
And somehow the importance of the zero mode, which I don't know.
So the importance of the zero mode is only, again, I'm not a quantum field theorist, and I'm aware that you are, so I feel a little bit daunted by this, but at least from what I understand of axiomatic QFT, the importance of the zero mode is that combined with the eigen decomposition of the Pauli-Jordan operator is what you need to define a Whiteman function.
When I was in this business, the whole axiomatic quantum field theory thing had pretty much failed after this Haag's theorem thing came out, which said that the only quantum field theory consistent with all the axioms of quantum field theory was a free quantum field theory.
Right.
So that was a big downer. In fact, I often quote that theorem in talking about evaluators in computational systems. And the only evaluator with no bugs is the evaluator which doesn't do anything.
Right. It's a bit like it's a Gödel theorem for axiomatic QFT.
Something like that. But the main point is that these axiomatization basically sufficiently ties the thing down that in the end it can't do anything. And I think what you're describing there is what was a big confusion. I don't think it's been unraveled of what the vacuum state is in axiomatic quantum field theory. And for example, whether there's a unique vacuum state, which was one of the assumptions that was made. It's probably not true for lots of interesting actual quantum field theories.
Right. But so, actually, I mean, the important thing is for our case, we only need a free field theory, in fact.
To do what? To do this computation of entropies.
And Hawking radiation.
Sure. I mean, those are free field theory stories.
Right, exactly. So I mean, yeah, I agree. If we want to do a more interesting interacting quantum field theory, then this is going to fail. This approach will not work. But
I see. So your point about the mode decomposition, okay, then I'm buying into your mode decomposition a bit more, because then you can actually do mode decompositions. The problem is as soon as the thing interacts, you can't do mode decomposition. I mean, the thing that happens in quantum field theory in curved spacetime is the modes get complicated, and that's why Hawking radiation happens and all these kinds of things.
Exactly. But the important thing is that both the entanglement entropy of a Einstein-Rosen solution and the Hawking radiation, Hawking-Bekenstein entropy, those are byproducts of purely free field theories in curved spacetime. The only thing non-trivial there is the curved spacetime. It's not the field theory.
Right. I mean, essentially, so the intuition there is it's a counting of states in curved spacetime as compared to flat spacetime. Right. So in our situation here, what is the counting of states? Because we must be able to have this explicitly. We don't have to worry about, I mean, in other words, the counting of states has to do with, in the multi-way graph, what are the set of possible branches that can be taken in the multi-way graph? That's what will determine the entropy in that sense. Right?
It's essentially like the geodesic ball construction in the hypergraph, but in a branchial graph instead.
Right. So the claim would be, and this is actually an interesting claim, which maybe you've realized long ago, but I hadn't realized, that the notion of entropy is basically branchial volume.
Yep.
So let me understand that for a second. But that's a very quantum mechanical notion of entropy. And I see. And the confusion in the classical case would be, in the classical case, you would attribute entropy to things because you say you don't know certain parameters of the dynamics. And so you say, because we don't know this, we will coarse grain together a bunch of states of the system. And so you could then say, I suppose, in other words, like in a hard sphere gas simulation, you could say, actually, this is interesting. So I see. Okay, so hold on a second. So we thought we were computing. So in that thing that chap at the summer school did last year of looking at the cellular automaton fluid business, where you don't have deterministic, where you have multi-way possible scattering events, right? You get a multi-way graph. You could think about that as a quantum process, or you could think about it as a classical process where you just didn't know enough to be able to determine which of those branches it goes down. And so you could think of that. You could ask, okay, you could say that the branchial volume is, okay, so then the question of the branchial volume relative to coarse-grained entropy is a question of coordinatization, yet again, is a question of the coordinatization of branchial space. That is right?
Yep.
So, but what you're saying for these, go ahead.
But just like with the ZX calculus case, this free scalar field theory is another case where we can cheat. We already know a priori what the coordinatization is.
Which is what?
Well, we know the spatial coordinates and we know the energy, we know the frequency modes, which is everything you need.
Fair enough. So in other words, what you're saying is, okay, so in that notion of branchial space, okay, what is the relationship between branchial space and Fock space? So in other words, you've got particle modes there, and the particle modes populate this Fock space, and what's the relationship between those and the branches in the multi-way graph?
I don't know.
Because that, I mean, okay, but the intuition we're trying to get is, I hadn't realized this. I think you've pointed this out, and maybe I did realize this before, but not as clearly, that this gives a notion of quantum entropy that is purely volume and branchial space. And I think the reason I didn't internalize that properly is because it's kind of messy when you think about the classical analog of that. That's a purely quantum mechanical phenomenon.
Right. And actually, there's an interpretation of the ADS-CFT correspondence that we can give that's based on that realization. Because so when you have an Einstein-Rosen bridge like this, the fact that its neck grows and therefore the cross-sectional, and it pinches off, the cross-sectional area of the neck decreases. That you can formulate purely in terms of a statement about the Riemann volume, the Riemannian volume element vanishing at the, essentially at the, or arbitrarily close to the space-time singularity, right?
Yeah.
Similarly, you can make entropy vanishing statements about Bekenstein-Hawking when you have a radiating black hole, or space-time entanglement entropy as the as the separation between the two anterior regions becomes infinite. And in a sense, what the ADS-CFT correspondence is telling one is that these notions, two of which appear to be quantum mechanical entropy notions, and one of which is a purely classical volume notion, in a sense, is telling you that those things should ultimately be the same. And this is a very concrete way of seeing that, because actually in this picture they are all volumes. It's just that two of them happen to be volumes that also have an interpretation as entropies.
Well, so let's go through this again. I mean, what we have believed forever is that the ADS-CFT story is a story of spatial degrees of freedom versus branchial degrees of freedom. And what you're saying is, if we look at essentially the spatially laid out, I mean, we have a multi-way graph. This is complicated, because what you've got is you've got something which is laid out in space. You've also got it laid out in branchial space. And the claim being made is that volumes in physical space are related to volumes in branchial space. And if I'm understanding, you're giving a concrete example on that neck. The claim is that even in branchial space, every different multi-way branch has to have that same neck. Is that the claim?
No, I mean it's part of the
true.
claim.
What's that?
It's not the whole claim.
Okay, well,
it's implied by it, but it's not the whole claim.
Okay. What's the rest of the claim? So I mean, the claim, there's a piece of the multi-way graph that is determined, and it's the neck. Right. For every branch, it has to have a neck.
Yep.
But keep going. What's the rest of the claim?
Well, the rest of the claim, as I say, is that there's a vanishing value of the Riemannian volume element at the arbitrarily close to the singularity, and there's a vanishing entropy value both for the Bekenstein-Hawking entropy and for the entanglement entropy. And so in our case, all that you're saying is, in one case it's a hypergraph volume element that's going to zero, and in the other two cases it's two versions. I
know this is what I was trying to say. That basically, by saying that the branchial volume element is going to zero, you're saying it is determined what happens there. Because that's what it means for the branchial volume element to go to zero, is that there's no diversity of branches anymore. It all has to be contracted into one branch.
It limits to something that would be determined if you could take the infinite limit, yeah. But it is not determined.
Right. But the question is why, I mean, so in other words, but the multi-way graph, in a sense, is necking. Okay, what do you think the multi-way graph looks like in this case? You think it's necking down just like the spatial hypergraph?
Yeah, well, I mean, in a sense, we need that to be true in order for holography to be the case. We need it to be true that there is some correspondence between the limiting geometries.
I know, but it's also probably true that the nature of these spacetimes is such that even though, when we allow all these different possible branches in the multi-way graph, that certain aspects of this are determined purely by causal structure effectively and are forced to have the same form. So that kind of compresses you in branchial space as it compresses you in physical space.
Sure.
But I mean, presumably, holography says more than just about necks.
Right.
Or doesn't it really?
Yeah, but my point is that, we're kind of we're slightly limited by the fact that holography, there are very few parts of holography that have actually been made mathematically formal. And one of the very few formal conjectures that I'm aware of is this ER equals EPR conjecture, right? Which is a completely rigorously defined statement about, limiting equalities of these two notions of entropy, which we can also, which we can supplement with an additional limiting statement about a Riemannian volume measure. That's a completely, formalizable.
Right. But I mean, in this, look, when we get to being able to not just do spatial hypergraphs, but being able to do multi-way graphs as well in the simulations, we should see something analogous to holography, because what should happen is, just as the spatial hypergraph, as you move away from some region, there's less and less determination of the spatial hypergraph. So similarly, as you move away from a region, a point in branch Hill space, there's less and less determination of the structure of the multi-way graph. And that is presumably that statement that both ways of moving away from a point in physical space or in branch Hill space have certain similarity to them. That is presumably the statement of holography.
Well, yeah, of course, but in as much as there is a statement of holography, which is exactly
No, I understand, but I'm saying we could actually make a statement of it, because we know there's a geodesic ball.
What I'm trying to do.
What's that?
Right, which is what I was trying to do. Yeah.
Right, but we can be more general than talking about ER equals EPR, and maybe you were doing that, which is to say, consider the spatial geodesic ball, consider the branchial geodesic ball, and compare those two things.
Right.
That's what I
meant when I said if we compare the Riemannian volume measure with the entropy measure.
Right, but so what will be true generically for us about the correspondence between spatial and branchial balls?
Well, the thing we would like to be true in the most general possible case is that in the instances where the spatial hypergraph has a limiting Riemannian manifold structure and where the branchial graph has a limiting projective Hilbert space structure, that the Riemannian volume measure and the branchial entropy measures have the same, obey the same asymptotic equations.
Well, if holography is true.
That would be the obvious extrapolation from ER equals EPR. Because ER equals.
Let me just go through that for 1 second, okay? So we've got and then I want to come to some other things, but we've got this geodesic ball in physical space that's that we're puffing out. We've got a similar geodesic ball in branchial space, right? Mm-hmm. And it potentially in this Hilbert space thing. Now, what was the statement you're making about you're somehow taking a logarithm somewhere?
Well, it's an entropy.
Yes, I understand. But you're making a correspondence between the volume of the ball in physical space and the logarithm of that ball effectively in branchial space.
Right. So as I say, ER equals EPR makes, in its extended version, makes a statement about the asymptotic relationship between the Riemannian volume measure in the neck and the entanglement entropy, which is essentially an exponentiated, branchial graph story. All I'm proposing is that we take the obvious extrapolation to that and we say that this is a principle that applies outside of the necks of Einstein.
No, I realize that. But
so what you're saying is that they have the same asymptotic behavior.
Okay, what I want to know is how you take the logarithm of a multi-way graph, which doesn't seem completely impossible to me. If it was a tree, it's pretty obvious how to take the logarithm of the multi-way graph. The logarithm of a tree graph is just a line graph.
Right.
Right? So the question is, in a more general case, can we imagine taking the logarithm of the multi-way graph? What does the logarithm mean? The logarithm means, as you look at a geodesic ball, you have an exponentially increasing volume in the geodesic ball. So the logarithm is just saying, instead of that exponentially increasing volume, so in fact, yeah, okay, so here's the question. Okay, basic questions, basic differential geometry question. What's the analog of curvature in the Hilbert space? So in other words, you have this exponential space. You have an exponentially growing space. So instead of r to the d for the volume of the geodesic ball, you have a 2 to the r volume of the geodesic ball. But now you want to have a curvature associated with that. What is the curvature associated with that?
Well, this is why the Fubini-Studi metric tensor is relevant.
Maybe I'll finally understand that. You've been talking about that for a year. Okay.
Right. But
what is
that gives you a way of essentially assigning a Riemann-like curvature to, projective Hilbert spaces.
What does it look like?
Now you're testing me. I haven't worked with it in a while.
It's been almost a year. How could that be? No, but I mean, but it's of the form a to the r, right? I mean that's the leading term of the volume of the geodesic ball. So the question is, what for us normally is r to the d times 1 minus something proportional to the Ritchie scalar. You're saying what is the analog of the Ritchie scalar for one of these Hilbert spaces? Is there a notion of Ritchie curvature? Or is it some completely different notion of curvature?
Well, there's an analogous notion of Riemann curvature, which is related to the non-commutation of operators.
Fair enough.
Yeah, undoubtedly there are scalar curvature invariants, but I don't know what they are yet.
But I mean, I think the formula we need to know is what the analog of the geodesic ball formula is for this exponential, for an exponential space.
Right, absolutely.
And then once you know that, so then the claim would be that treating that as an entropy. So you're taking the logarithm of that. So the claim would have to be, okay, so I'm going to make the claim that the claim is, if you take the log, okay, let me just think about this in a very naive way. So the log of a to the r times something has got to be r to the d times 1 minus, Riemann scalar, Ritchie scalar times r squared or something, right? So first question is, how do you take the logarithm of 2 to the r and wind up with r to the d? So the answer to that is, how do you do that? That's a naive question, but how do you do that? So you have to take the log of a to the r and wind up with r to the d. Well, okay, so there's a bit of math to do here. All right, I finally understood this. This is good. This is, and now you've convinced me. I finally, I've had this book about Fisher information sitting on a table for the last year. Should I be looking at it now? Does the Fisher information is that the same metric thing?
Yeah, up to a factor of 4. The Fisher information metric is the same.
Well, so does that mean that Fisher information has a curvature?
Fisher information can be used to describe a curvature, yeah.
Very interesting. Okay. So, and in what sense, it feels like the difference between a Lie algebra and a Lie group or something of, you're exponentiating this thing to get this full branchial, full multi-way graph.
Right. What we really want is something like the Baker-Campbell-Hausdorff formula, but for multi-way systems, but we don't have that.
Why would that help us? So that's giving the exponential of a commutator or the exponential of a product of operators as a sequence of commutators.
Right.
Why does that help us?
Well, because so what we want to know is when you have a bunch of, say, volume measures or something on different spaces, we want to know essentially how they combine in branchial space. And if we could treat those like differential operators that appear in the Baker-Campbell-Hausdorff formula, then we could actually do arithmetic on them, which I don't think we can do right now.
Yes, that seems like a doable piece of math. All right, let's keep going. Anyway, we haven't even finished going through your paper here.
Right. Anyway, sorry. Yeah, that was irrelevant. Okay, this is all information about extraction, about the Moncrieff formalism, extraction of Weyl scalars. Okay, so here we've got binary black hole collision, 2 equal mass Schwarzschild black holes. This
is again still with a scaffolded setup.
Yep, they circle each other. You get the right convergence properties. They eventually merge. This is what their causal structure looks like.
Is it surprising that your few nodes across the black hole still gives you reasonable answers, or is that not too surprising?
It's a bit surprising, but I mean, bear in mind that we are refining, right? That the solution is finer in regions of high curvature and coarser in regions of low curvature. So that helps us a bit. But anyway, okay, so then there's the coordinatized versions of that. This is what we eventually, after the ring down phase, that's what it settles down to, just an ordinary Schwarzschild.
What happened to the gravitational waves? Can you see gravitational waves?
We can. So we can't see them very far, but what we can do is, what I'm doing here is I'm setting up a hypersphere, an exterior hypersphere surrounding the whole setup, and I'm extracting the 4th order Weyl scalar, psi4, and then just plotting out the real part of one of the modes, the L equals 2, M equals 0 mode of the Schwarzschild of the radial coordinate r times psi4 extrapolated on that sphere.
What is that a quadrupole deformation of space-time or something, or what is that?
Yeah, it's so psi4 is giving you essentially the modes of the transverse perturbations of space-time.
Okay.
Sorry, I should say the outgoing transverse perturbations. I think the ingoing, I forget the identities of the Weyl scalars. Jose might be able to remind me. I think psi2 is the incoming and psi4 is the outgoing, as I recall.
But physically, these are tidal deformations of space-time. Is that right?
Yes.
Okay. And so that's the magnitude of the tidal deformation. Presumably, you could also compute the polarization of the gravitational wave and things like that.
Yes, yeah. So actually, in order to do this extraction, this is how the Moncrief formalism works. You have to split it up into plus polarization and cross polarization, and then combine them. But yes, so we could leave them separated if we wanted to.
Do gravitational wave detectors have a chance of detecting polarization? They do, don't they?
That I don't know.
I don't think the current generation do, but I think the space-based one does. Does Jose know?
I cannot say for sure, but I think eventually it should be possible to detect it. Yes.
It sounds plausible.
Okay. Okay.
Anyway, yeah, this is nice because I mean, all it's doing is it's showing sort of convergence of to the right gravitational wave signature. Okay,
Well,
this is.
do all gravitational wave mergers? I mean, there are now 50 mergers that have been seen, right? Do they all ring down in more or less the same way?
I think it depends a little bit on the. Okay, no is as far as I know is the answer, because I think it depends a lot on the initial data, right? I think
So
the ring
are
down.
your Schwarzschild black holes the same size there, or what?
Yeah. These are all equal mass things, but I think if one of them was like a billion times heavier than the other, the ring down would look very different, I suspect.
But so can you compute? Have you done the computation for just different mass ratios of the black holes? That'd be nice to see.
Yeah, it can be done. I haven't done any systematic investigation of it.
I mean, I don't know. Presumably, it's known in the standard general relativity literature what the different, ring down. I mean, presumably, roughly, if you have two galactic center black holes, merging, it's going to take a lot longer to ring down than a few seconds, presumably.
Right. Yeah.
I assume, at least. I mean, I think it has to, because the speed of light propagating across the region of the black hole is much longer than that.
Right. Yeah.
How big is the galactic center black hole? Anybody know? I mean, it's about 10 to the 5 solar masses, I think. But how big is that?
That's
right. Let's ask Wolfram Alpha. It might know. It certainly should have data on black hole 10 to the 5 solar masses.
Right. So solar mass, it corresponds to like 3 kilometers. So it should be.
Actually, it has a horizon radius here. 2.9 times 10 to the 8 meters, which is 183,000 miles. So 1 light second, roughly. Okay, so 46. So it's about half the solar radius.
That's small. Black holes are small.
They are very small, but I mean, the usual one is like a kilometer or something. So it's
right.
Let's see, 1 solar mass black hole. If you type it into Wolfram Alpha, it should just work. 1 solar mass black hole. Always good to make sure. Let's see. Horizon radius, 3 kilometers.
Wow, titchy.
It is. It's like a neutron star is a bit bigger than that.
Right. Anyway, sorry. Yeah, these are same tests, just with Kerr black holes. So you get some slightly funkier. This is quite cool, where you get the really, really stretched thing along that axis. The solution becomes almost sort of one-dimensional during the initial merger, and then post ring down again, you get just an ordinary stable Kerr black hole, where you get conservation of angular momentum, which is unsurprising and good to validate. And here's what the gravitational radiation looks like. Anyway,
what happens if the angular momenta add? What happens if you go from a subcritical black hole to something that would be a supercritical black hole?
Yeah, that would be cool. I want to run that simulation. It's not in this paper, but yeah, that would be really interesting, because then your question about the separation time would be relevant, right? Because then you actually, then the separation isn't just an initial data thing; it's an actual physical effect.
What happens in that case?
So what has been observed in simulations is that if you have two black holes orbiting each other with too much angular momentum, they will keep orbiting and orbiting, emitting gravitational radiation and angular momentum until there is.
I see. Until they go subcritical, until until the sum of the moments is subcritical, and then they'll merge.
Exactly. So, for example, there have been very nice simulations in which you start with two orbiting black holes, and you have the angular momenta of the black holes aligned or anti-aligned with the angular momentum of the orbit. And then if they are anti-aligned, so the total is near zero, they collapse very soon. But if they all go in the same direction, so there is a lot of angular momentum, they orbit a lot of times.
Right.
It's very interesting.
But so, okay, so, skipping ahead because we're going to run out of time here. I mean, the basic point is you managed to do this whole same thing with
ordinary Wolfram model evolution. So this is, extracting, spatial and causal curvature information in the usual way, extraction of sectional curvature tensor from which we reconstruct the Riemann tensor, blah, 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 blah.
How critically does it matter that you have causal invariance in the underlying rules? I bet you're not really using that. I bet you're just using some kind of equilibrium property.
Well, this rule is causal invariant. How important that is, I don't know. Okay, so I should say a little bit about how I found this particular rule. All that I did was, so we have causal invariance testing code that was written a while ago, and I've got modified ones that check not just for confluence, but also for partial causal graph isomorphism. I have a very, very heuristic sort of ergodicity tester, which all it's doing is it's looking for the opposite of vertex transitivity in the causal graph. It's looking for sort of, for neighborhoods in the causal graph to be kind of maximally different. And it's using that as its heuristic for weak ergodicity. And then it's also testing dimension preservation. It's just propagating out the causal graph for some distance, and it's seeing whether the dimension shows any sign of stabilization. So I had tests for just determining whether those three conditions were met, and I just did a systematic search of the 4.2 to 4.2 rules, and this was the first one I found that passed all those tests. And so it was the obvious kind of case to look at, because we know that if those tests pass, that rule should satisfy the Einstein equations in the continuum limit. So then what we do is we produce the hypergraphs by this rule, which are shown on the right. We produce the associated hypergraphs produced by solving the Einstein field equations, and we show that the two evolutions indeed converge to the same limiting spacetimes. So this is the causal graph produced by Einstein field equation solution. This is the causal graph produced by Wolfram model evolution, and the conformal structure of the two solutions, they both converge to the same continuum limit.
In some vague sense, at least, right? I mean, okay.
Not in a vague sense, as far as I know.
Well, I mean, so what can you? I mean, those pictures. Are you saying you can actually make measurements of curvature tensors for those pictures?
So all I'm doing is I'm looking at what is the conformal curvature at each point in the causal graph.
Okay, fair enough.
And then showing that there's what pictures like this are really showing. I mean, this is showing the Hamiltonian constraint, but there are associated convergence analyses for other quantities too. And it's showing that effectively that the Hamiltonian constraint, and therefore the lapse constraints, and therefore the conformal curvature constraints, are all in these two cases converging to the same answers as the causal graphs become larger. So in the case of the numerical analysis, it has roughly fourth order convergence. In the case of the Wolfram model evolution, it has roughly second order convergence. But that's just, I think, because this was the first rule I found, and undoubtedly there are others that have more desirable convergence and stability properties, but we haven't found them yet. This is the first example I found that explicitly satisfied the Einstein field equations.
I mean, this is deeply reminiscent of the fluid mechanics situation, because you've got a rule there that just sort of mixes things around. It is a somewhat conservative rule, as in certainly conserves the number of atoms of space, it mixes things around, and that's the life of computational irreducibility. It doesn't matter much how the mixing around works. It's always going to give you more or less the same continuum limit behavior.
Right.
I mean, it would be interesting to understand the space of rejected rules, to understand.
Yeah, I mean, so I mean, it's entirely possible that there are some, for instance, that fail the causal invariance requirement, but still produce good convergence to the Einstein equations.
Sure.
and someone should look into that. I might add it to the summer school project list or something.
Yeah, I think I'm understanding that space of rules seems useful. It also seems useful to understand if they're essentially higher order rules where you're using more, relations in the rule, and whether that gives you some different, convergence rates and things like this.
Yeah, it's possible that just by ordaining, by making these slightly more ornate, you might be able to improve stability or something.
Right. Okay, keep going. So then
gravitational radiation extracted in the same way, but now just using the hypergraph topology, and we get the same profile, but with a lot more jaggedness because there's obviously less information. This is the Kerr black hole case, again simulated using Wolfram model evolution on the right. Same conformal structure story. Post ring down, we get the same solution. Convergence properties are the same. Gravitational wave extraction again yields the same limiting profile.
All right. So we've now got to Okay.
Sorry. Yeah.
Well, let's see. Okay. People are asking for animations. I'm also asking for animations. Are they makeable?
I have one which I tweeted a few months ago. Let me see if I can fish it out. I made an animated GIF thing of a black hole merger, but
well, okay, but independent of that, let's talk about. You could bring back up some of those pictures because they're relevant. I mean, I want to talk about what this means. Okay, I want to talk about situations in which essentially the numerical analysis fails, and you see the underlying structure, right?
Right. Sorry, yeah, just quickly on that particular issue, let me share this. That's what a black hole merger looks like animated. But actually, this was from a while ago before I optimized the code in a bunch of ways. So we should be able to produce much higher resolution versions of this visualization now, which might be nice.
So recalling the color coding is the curvature.
Yes.
It's the
Schwarzschild conformal factor. Yeah. So this is one that's actually produced using that's done in the numerical analysis way. What we can now do is also produce the ones that are using Wolfram model evolution, and we should be able to show those side by side, and that would be kind of interesting.
That would be interesting, but I want to see some gravitational waves produced here.
Yes.
I mean, so one of the things you're not doing here is this is not embedded in the background space-time. This is just the local region. It's as if the whole universe is being represented with this this is the whole universe, and it's just a black hole merger, so to speak.
Right. And so, yeah, that's an important point to clarify, actually. So I go into this in the paper a bit. So therefore, in order to extract the gravitational wave information without having to simulate a huge background space-time, what I'm doing is I'm applying what are called the Sommerfeld boundary conditions, or the radiative boundary conditions. So after the thing merges, I then take the boundary region to be the sort of to be the hypersphere on which I'm extracting the gravitational waves, and then I set up the boundary conditions such that the gravitational waves essentially propagate out through that hypersphere as though there were a background space-time. But that's kind of a mathematical hack, and if we can do this with more computing power, then it would be worth absolutely doing this with a lot, with these things embedded in a larger background space.
Well, why don't we do it? I mean, how much did you just do this on your laptop?
I was doing it on a MacBook Air, which is probably not the optimal.
Oh, for goodness sake! I mean, if you've got the code, why don't you at least run it on some bigger computers that we have?
Right.
I mean, is it parallelizable at all?
Yeah, it should be. Yeah.
Well, I mean, you could use Jesse's whole AWS framework, or you could use some computers that we have lying around at the company. But you should run it. That's ridiculous to have the black hole merger run on a MacBook Air. That's
right.
Seems crazy. All right, let's see. We're unfortunately going to run out of time here, which is really a shame. But let's talk a little bit about, okay. So one feature here is, where do we get something where weird things can happen? So for instance, in your scaffolding, could you scaffold something which is not four-dimensional space? Do we have any way to do that? Do we know a way to do that? Do we know a way to sprinkle in 3+epsilon dimensional space, so to speak?
Well, complicated question. So the only way I know how to do that is, and we tried to do this at the winter school and it didn't work so well. But I'm still optimistic that this approach could work. I think it just needs more effort. is we sprinkle into an integer dimensional space, and then we just add essentially stray hyperedges or stray causal edges.
Yeah, we've tried that. Doesn't work well. I mean, it's the same problem that we had, back, a year ago, trying to do more than a year ago, before you had figured out, causal set-based sprinkling, when we were trying to do intrinsic curvature, when we were trying to create a Schwarzschild solution-like thing, it didn't work very well. I mean, I suspect we'll be better off just growing the thing algorithmically.
Right.
In other words, taking a hypergraph which we know, which we know grows a certain dimensional space. Various people are commenting on the outrage of hacking the universe on a MacBook Air. I feel a little bit strange here because I just got myself another 64 cores of and I'm now routinely running my little tiny experiments of systems much simpler than the universe on my now 157 cores. And so I think we need to make sure you can run your simulations on a larger computer.
Right.
Which should be very easy, either using the batch submit mechanism to cloud provider or using some local. Okay. Anyway, that's a very practical problem. That's a solvable.
If it were really a bottleneck, I could have used the Cambridge supercomputer network or something. But fortunately,
right.
for these simulations were sufficiently small that it wasn't a problem. But I think if we want to go larger scale things, including background space-time, then it's more of a problem.
All right. But anyway, back to this effort to try to understand. I mean, so the question is, where are places where you are seeing sort of, what are the analogs? Where do you see the analog of hypersonic flow, basically? Because that's what we need in order to see. That's where you see in fluid dynamics. That's where you see the breakdown of standard fluid behavior is in hypersonic flow. So the question is, what's sort of the analog of that in the relativistic case? Is it something, I mean, is there a place where we expect, for example, a small number of causal edges connecting things? Is there a place where, do we expect some kind of noise in the gravitational waves associated with, so eventually, one thing that happens with discrete systems is you have shot noise from the fact that the thing has, is making, discrete, they're discrete pieces rather than it being a pure continuum value. So the question is so one question would be, how big is the shot noise for gravitational waves produced by these black hole mergers? That would be one question. And what would cause there to be more shot noise?
So one place where I think we might be able to see discretization effects, or at least where I saw discretization effects in the solution outcomes, in the simulation outcomes, was, so in here, when we have, black holes, Kerr black holes that are very close to criticality, you have, because of the separation between interior and exterior horizons, you get actually very few hyperedges and very few causal edges appearing in this interior region here, right? So because of that, during the ring down phase, you would expect then the gravitational radiation would not be coming, it wouldn't be sort of isotropically distributed. The gravitational radiation would come out with a slightly lumpy non-isotropic distribution as a consequence of the fact that you only have comparatively few causal edges there.
Wait a minute. I'm sure that the angular distribution of the gravitational radiation it's not a spherical wave, right? Even in the best of times, it's got some kind of complicated antenna pattern, isn't it?
Right. But if you knew, I mean, this is now a very non-physical hypothetical example. But if you knew the angular momenta and the masses of the black holes that were merging, and then you looked at the fourth order Weil scalar, extracted across this hypersphere, then you would be able to predict, theoretically, assuming continuum spacetime, what the angular power spectrum looked like for the gravitational waves. Yeah. But what you would see in this case is actually that the angular power spectrum was not that, because it would have regions where it were much lower because there was a lack of edges, and it would be regions where it was actually correct, which are where the hyper edges were.
Let's understand that for a second, okay? What does a lack of edges do for you? In other words, when you are generating a gravitational wave, when you, quotes, don't have causal edges, the causal edges represent are orthogonal to the characteristic lines, yes? Or are they, no, they are the characteristic, which
they
way?
are the characteristic lines.
They are the characteristic lines.
Yeah.
So to say that there's a lack of causal edges is to say, so in terms of the wave fronts, what does it mean that there's a lack of causal edges? There's a lack of characteristic lines, but so what?
So there's no information that propagates from certain regions of spacetime to certain other regions of spacetime. It's as though there's a sort of horizon there, even if there isn't actually a horizon there. So like what I essentially mean is, so if you take an example like this, say, here, if you made a perturbation on the interior here, it would propagate out to the whole rest of spacetime, no problem. It would propagate out in every direction pretty much, because there's a good sort of continuum approximation here. But here, a perturbation you make here is not going to propagate to this region of space, and it's not going to propagate to this region of space. It's only going to propagate, the here, 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 and here. So if you imagine extracting an angular power spectrum, these regions here are going to be blank, pretty much.
Okay, but so let's talk about the continuum version versus the discrete version here. So in the continuum version of a close to criticality Kerr black hole, my guess is that there's a complicated angular spectrum of the black hole radiation. Maybe Jose knows what it is. Do you know what it is? I don't. I mean, I'm assuming that these black holes are spinning around. So I'm assuming, perhaps incorrectly, that there is more intensity going in the outward direction than there is in the direction of the in the spin vector direction.
So these patterns have been computed and simulated, and of course the plane of symmetry and the axis of rotation introduce a strong asymmetry in the result.
But so what happens? Along the rotation axis, you get less gravitational radiation, is that true?
Yes, I think so.
Okay, but so what Jonathan is saying is, in this case where you have a lack of causal edges, that lack of causal edges will be, if I'm understanding correctly, will be concentrated also along the rotation axis. Is that true? Yes,
but the important point I'm making is that some of it will be random, right? So the fact that you can take an angular power spectrum in the continuum limit is a consequence of the fact that there are causal edges going out in all directions, right? But once the density gets low, there will be certain angular regions where there just aren't any causal edges to carry to carry the wavefronts.
No, I understand that, but you're saying that will happen along the direction of the rotation axis and not in the direction of the in the orthogonal plane. In this picture, at least, that's what's going on.
It'll happen in all directions. It'll happen more, I think, in the direction of the rotation axis.
And it will happen in all directions because of the separation, because essentially of this necking phenomenon. Is that true, or something like that?
Yeah, something like that.
And so what would you expect to see then?
So my prediction, I don't know, I haven't tested it. My prediction is that then you would expect to see something that looked like the true angular power spectrum, but which had weird kind of blobs missing, if you see what or sort of it would have dark patches where you wouldn't expect dark patches.
I wonder whether it would have dark patches or whether it would simply have blotches, which would look quantum mechanical, so to speak. In other words,
something like that, yeah.
Well, in other words, it would have shot noise because it has a lower density of interesting. We unfortunately are running out of time here because I'm supposed to go off and do something different in a few minutes, and this was just getting interesting. Okay, so another question here. I mean, I think you really need to make these dimension measurements because, for example, let's say that you have these spinning black holes, even just to not forget mergers, a spinning black hole, and does it have dimension fluctuations around it? If you measure the dimension of the hypergraph, what is that dimension? You can measure the curvature and you get some value, and that curvature value should agree with the Einstein equations. But the question is, what is the spectrum of dimension fluctuations? Right? It will have dimension fluctuations. It will not be precisely at a microscopic discrete scale. There will be dimension fluctuations. The question is, how big is the tail of the dimension fluctuations?
Yeah, I mean, the reason I find this question conceptually hard to answer is that everything we've done so far with the, both in the numerical analysis side and with the Wolfram model side has been assuming fixed integer numbers of dimensions. That's how we extract curvature information.
No, I understand that. I understand that. So the question would be, assume you see, this is where everybody who does numerical analysis always is so nervous about pushing it to the, you see, this is where you have to have somebody else who's not been involved in numerical analysis, who just says, what would happen if you made, I mean, it's like people doing cellular automata and saying, but if you do these discrete cells, you will get wrong results because they will have, because they won't go to the continuum limit correctly. And it's like, well, that's the point. Anyway, but in this case, let's just take your simulations as they exist right now and ask the question, if you were to measure dimension in different regions around the thing, what would that dimension be? And what will happen is, as you measure those geodesic balls, some of them will have nice dimension 3 or however you're setting it up. And some will have dimension 3.1, some will have dimension 2.9, etc.
Right, but what I'm trying to check is that when you say measure the dimension, are you assuming constant curvature there?
I'm assuming that you are at a particular position in your simulation, right? And you might do an ensemble of simulations, but I'm saying at a particular radius, from the black hole center, you could maybe do it, in some symmetry related points. So you just get more points, but it doesn't really matter. At some symmetry related point, let's say it's a Schwarzschild black hole, then it would just be at any position at certain radius.
I'm asking a much, much more basic question than that, which is, we have this problem, right? Which is that the Riemannian volume, when you take the Taylor expansion of the Riemannian or the Lorentzian volume measure, you have an equation with one known and two unknowns. The known is the volume measure, and the two unknowns are the dimension and the curvature. For curvature, we get around that by saying we know the dimensions and we compute the curvature. What I'm trying to work out is, how are you proposing to solve this equation with one known and two unknowns? Are you proposing that we assume the curvature is like 0 everywhere?
No, I'm proposing a purely parasitic approach. That is, you've already got solutions, right? You've already got definite.
Okay, right. So what you're proposing, it would not, as I understand, that's the thing I wanted to check, right? So your proposal would not work in the pure Wolfram model case where you don't know the a priori curvature information. It could only work in the case where you know the space-time, because then you just.
Oh, I don't understand. Once you do your whole thing, you just do one of your calculations, and you happily do the calculation. You get something which you think is an accurate Schwarzschild black hole. Okay.
But
now, what I'm saying is,
am I doing this calculation with Wolfram model evolution?
Yes.
Okay.
Yes. So you get what you think is an accurate black hole. You do all your diagnostics on it. Looks good. It's got the right curvature, and it's got the right curvature given that you assume it's dimension 3, right?
Fine. Yep. Okay.
And then you simply say, well, by the way, just take that simulation and just actually measure in more detail the local dimensions, because what you'll find is a distribution of local dimensions. It won't be always precisely 3.
How am I measuring the local dimension? If I measure the local dimensions, assuming the curvature information I've already computed, then I'm just going to get back the dimension that I assumed to compute the curvature information, because it becomes circular.
No, I'm saying you've computed the curvature. You've got a definite hypergraph. You've got a definite sequence of hypergraphs. You say, these look good. They correspond, assuming dimension 3, they give the right curvature. Mm-hmm. Okay. Now say, just take those hypergraphs as, original hypergraphs, forget what you measured about them, and remeasure the dimension in those hypergraphs.
How?
Assuming nothing, right?
But so how, again, I come to this question. How do you, the only piece of information you know is the volume, and the curvature and the dimension are now unknown. So how do you extract the dimension without making assumptions about the curvature?
I don't understand. You can compute the dimension just by looking at volumes of geodesic balls. You don't need to know anything about volume measures. I mean, you don't need to know.
No, the volume measure is the volume of the geodesic ball, right? And the Taylor expansion has up to second order 2 unknowns. It has the dimension and it has the curvature.
No, but I'm saying you just use the graph distance. Okay, maybe this is the point that you just use the graph distance to determine distance and then you simply do the direct computation of the geodesic ball volume.
I understand all of that, right? And that gives you a volume measure that equips every point in the hypergraph with a volume measure.
Yep.
How do I compute a dimension from the volume measure without implicitly making curvature assumptions?
You are. Yes, you would implicitly make a curvature assumption.
So I come back to my initial question. Am I implicitly assuming constant curvature, essentially zero curvature everywhere? Or what curvature assumption am I making?
That'd be fine. If it's small enough radius, if you are able to extract the dimension over a small enough radius, it's enough to, it doesn't matter what the curvature is.
So then I'm just doing a log difference estimate.
That's right. Yeah, that's right.
Okay. Yeah, fine. That was my only question. Yeah, I want to know.
Yes, that's all I'm suggesting.
Am I just assuming constant curvature? Yeah, that's fine.
Right.
Okay.
But the point is that what you will get from that is a distribution of effective dimensions.
Yep.
Right. And my question is, what on earth is that distribution? Is it Gaussian? Does it have power law tails? What does it look like?
Yes. Yep.
And in particular, in that dimension perturbation, in that dimension distribution, as you look in different regions around the black hole, what my guess would be that close to the horizon, the dimension fluctuations increase.
Right. Right.
Just because more's happening there.
Yeah. I mean, it's probably the standard deviation of the dimension fluctuations is probably a good heuristic for places where the numerical scheme converges poorly.
Indeed. Absolutely. That's exactly what we're looking for.
Right.
Because the numerical scheme is not a numerical scheme. It's the actual physics as opposed to as opposed to some crazy continuum, approximation to the physics. I mean, this is the same thing. It's like you could say in hypersonic flow, the numerical scheme for the Navier-Stokes equations converges slowly. And that's why you have, the kinds of, chemical-based shocks that you have in hypersonic flow. So, I mean, that's what we're looking for, is exactly those places where, and so, the question then would be, so we can presumably simulate photon propagation through one of these spacetimes.
Yep.
That's presumably quite straightforward. So then the question is, as the photon propagates through this region of dimension fluctuations, what does it do? And we should be able to compute that wavefront, right? Because the wavefront is you're just going successive. I mean, it's just it's the story of, it's a nice conformally invariant thing that's propagating through the space-time. So one's assumption is that just like there's gravitational lensing, where, that you would have essentially gravitational dispersion, which would probably look a lot like gravitational wave turbulence.
Yes, something like that.
Right. So, I mean, the question then is, if you have dimension fluctuations, so how do you distinguish gravitational wave? Well, okay, there's a question. Does anybody see gravitational wave turbulence? That's the first question.
Numerically, absolutely, yeah.
Yeah, but does anybody know if it's real?
I am not sure.
Jose, do you know?
I don't know. I mean, turbulence in general relativity is tricky.
I understand. Yeah. It's tricky in fluid dynamics as well. Back when I was studying these things in the 1980s, I would ask people all the time, because I could see it in my cellular automaton stuff. And I would say, do you see it in numerical analysis? And they were always very, very, very squiggly about it, because they always believed that when they were seeing turbulence, most likely it was a breakdown of the numerical scheme and not actual fluid turbulence. So this is why, this is what's really cool here, because again, same thing as with cellular automaton fluids, because we have an underlying model, there's no numerical artifacts. It's just what the model says. And so in other words, if there's the analog of if there's essentially space-time turbulence, then, you will get, it will be what it is. And it's not just, the numerical scheme broke down.
We have continuum artifacts, which is a slightly different.
Yes, that's right. As opposed to, so then the question is, if a photon propagates through a region of dimension fluctuations, AKA, or in general, I mean, what will that do to it? And where would that, I mean, where's the best place to look for that? So the thing we want to do is measure, presumably, the variance of the dimension, and or I mean, what we're measuring is essentially quantum gravitational effects or discrete gravitational effects, not really quantum at this level. It's simply discreteness in space-time. So then the question is, where is that discreteness most obvious? And is it the case that, for example, what you want to do is look at a photon that propagated close to critical Kerr black hole, for example?
Right. So I have one suggestion for a concrete thing we could do in that regard, which is, so if you take, well, let's just do it on space-like hypersurfaces, because that's probably, actually, no. Let's do it for causal graphs, because that's probably the easier case. If we sprinkle, a bunch of causal graphs into known Schwarzschild solution spacetimes, then there's going to be a natural, then in that population of sprinkled spacetimes, there's going to be a natural distribution in dimension perturbation, say near the horizon. So one thing you could then do is, given that population, because what you're really asking about with respect to kind of effect on photons and things is, if we tracked a single causal geodesic, what does a region of dimension perturbation or something, what does that do to the endpoint of that, to the address of that geodesic, if you like?
Yep.
So what you could then do is say, well, let's send a geodesic kind of within a certain distance of the horizon for the lowest, for the space-time with the lowest value of the dimension perturbation, and then for the space-time with the highest value, and then just, and do that for a bunch of these different sample spaces and just compare them. Keep all other aspects of the geometry and the trajectory the same, so we know it's not gravitational radiation in the conventional sense. We know it's not just, a curvature effect.
Look, I think physically what's going to happen is the wavefront is going to get broken up. So it's going to look like random scattering of the light. In other words, what started as a coherent, I don't know whether there's enough coherent, I don't know whether the situation arises where you have coherent radiation, say from an astrophysical maser, that can be, can have sort of a glancing interaction with a Kerr black hole. And that would give you, I don't know whether that, that's a microwave photon or something interacting with, so then the question then is, what can one detect about, what one would expect? Okay, so if it's a coherent, well, one question is just ordinary photons, and what I think it will look like is just plain scattering, just like scattering from a random medium.
Right.
I think it will be hard to distinguish from, go ahead.
I was thinking that in that situation, the interesting effect is radiance, super radiance, so extracting energy from the ergosphere. But as far as I know, even though general relativity can become very nonlinear, turbulence in a vacuum solution has never been observed. Of course, if you put a turbulent fluid in space-time, I'm sure the metric is going to inherit that turbulence. But by itself, I don't know of any turbulent solution.
Right. The superradiance thing, the question is, does that superradiance play into dimension fluctuations in any way? Look, one feature of dimension fluctuations is the inverse square law isn't true anymore. But if the source is at infinity, I don't think that makes much difference. Although, well, it just has to be computed. This is one of these things. And I suspect it's as easy to compute in the explicit in these explicit simulations as it is to compute it by traditional physics of looking at, because you've got to, this is propagation of light in a random dimension medium.
Right.
Here's what you do. Think of Huygens principle, okay? So Huygens principle says every point on the wavefront is a source of can be thought of as a source of a spherical wave. This is the way to do it. So what you do is, yes, it's the source of a spherical wave, but it's a source of a spherical wave with a random number of dimensions. So any subsequent point is the result of a distribution of, instead of 1 over r squared, it's 1 over r to the d minus 2 or whatever. So you should be able to compute that as a sort of generalized Huygens principle. And then if you assume, right, so then what you're doing is you're assuming instead of the wavefront being one where everything is a spherical wave. Everything is a spherical wave in d dimensions with the sprinkling of different d dimensions for different points. So that absolutely would be computable. And I wonder what the heck that would look like. I wonder what's that?
I like that. That's a good idea. It's like it gives one a continuum way of computing the same quantity, which is kind of cool.
Right. But I mean, so the question then is, what happens with different distributions of, I mean, one's immediate assumption would be it's just like Gaussian noise and it will just scatter the light randomly. But I wonder whether that's actually true, or whether the thing is weighted in some weird way where, lower dimension produces, because it has, it's easy to compute. Okay, well, that's interesting. But so the real point here is, to find places where you might think that the only effect, yes, here's a way to think about it. The elementary length is very small compared to, let's say it's 10 to the minus 90 meters. That's a very tiny elementary length. Where does that elementary length essentially get stretched in a world of black holes? Where does that elementary length get stretched so that, in other words, for example, in an almost critical Kerr black hole, is there a place where that elementary length is getting stretched out to be something that is macroscopic?
Well, yeah, I mean, in a sense, that's what leads to the appearance of the ring singularity in this discrete, in this discrete model. Right? You're getting an elementary hyperedge that's being stretched across the entire length of the ergosphere, which is no longer, so it's very much not elementary anymore. It's a macroscopic thing.
Right, which is to say that the reason that's happening is that when you assign a size to the ergosphere, it's based on it. I mean, I guess you can think about it in terms of some tipped light cone thing.
Well, the point is that when we compute space-like distances, when we compute space-like or time-like distances, we are assuming a non-co-rotating reference frame. Right, our standard construction of the metric assumes a non-correlating reference frame. The point is, as the thing becomes supercritical, that becomes a less and less good approximation, and so the gap between the sort of true distance in the actual physical co-rotating reference frame and our numerical approximation to the distance, assuming a non-co-rotating reference frame, that discrepancy becomes arbitrarily large, and that's essentially what you're seeing.
Right. So the question is there an analog? So here's an example of something really interesting that could happen. Is an analog of superradiance coming from different dimensions. So in other words, superradiance is just feeding energy from the rotation of the black hole into radiation that's having a glancing scattering around the black hole. But what if effectively what's happening is, I have no idea what happens to energy conservation when you have this. I have no idea. What does it do? How does energy conservation work when you have different dimensional spaces? Because even the definition of energy, if it's a definition in terms of causal edges and causal edge density, even that's going to get messed up there.
Well, in the relativistic sense, energy density is okay. Energy conservation is fine. It's momentum conservation that becomes a bit complicated, because the energy conservation, which is just the Hamiltonian constraint in the ADM, in the metric decomposition, that's given in terms of, as I say, causal edge distance. That's just single, time like GD6. That doesn't really care what the dimension of the ambient spacetime is so much. I guess the causal edges will get deflected a bit or something. But the thing that really matters is when you define your shift vector, you're essentially assuming a fixed number of dimensions, and that's the thing with respect to which you're defining the linear and angular momentum constraints. So understanding, I think, momentum conservation
right, which is also a story of scattering, because scattering is a change of momentum. That's what it means to scatter something. Is it was coming in one direction, it got kicked in another direction, and so getting kicked in another direction when there are many more directions to be kicked in because you're in higher dimensional space. I don't know what effect that really has. And I think this higher dimensional Huygens construction is probably a reasonable way to think about that.
this may be a very naive question, but I would have thought surely this is something which the people working on like supersymmetric phenomenology must have thought about, right? Is that
I bet they haven't, because they don't have the same situation. They don't have continuous variation of dimension. All they have is the rolling and unrolling of integer dimensions. It's different.
yeah, okay, fair enough.
I think it's really different. I mean, I think that the concept of a continuously variable dynamical dimension has just not been considered, so far as I know. And we're finding out one reason why is because it's kind of hard to work things out in that case.
Right.
Although I do like this Huygens idea, because that idea is quite tractable. I mean, it uses extremely primitive, mathematical physics in a sense from the very earliest days of mathematical physics, but that means it's more robust, so to speak.
Right.
All right, I better go to my next and completely different meeting. But all right, we're making slow progress here. This is we're going to get this. Well, go ahead.
We should do this again, but with some, with some serious astrophysics type people, observational astrophysics people.
Yes. Why don't we do that? Why don't we plan that even for next week or something? Let's pick our get some. We have some good volunteers actually from some. Are we going to get? Should we get observational ones or should we get theoretical ones? What do you think?
I don't know. My personal feeling is that the thing we're lacking right now is people with experience of actually setting up gravitational wave experiments and stuff. Because I guess theoretical astrophysics people would be helpful for these naive questions about angular power spectra of gravitational waves and things.
Right.
Both
but
are
I
useful.
think there's more stuff to do with actual. These things like. Can you see occultation of an astrophysical maser by a Kerr black hole? I don't know. That's a question that's a sort of detailed question about some. It might be that I don't know what that. It's hard enough to see the gravitational masers, and it may just be that the lining up two very small things, in the sky is very unlikely. But just like I worked out that the merger of two black holes of the comparable to the size of the center of our the one that's center of our galaxy, that's probably happened on the order of 3 times in the history of the universe, which I think would be it's just like be there for the sort of size of the sun sized black holes merging. It's probably, a dramatic event in the history of the universe, rarely to have happened. But that's no good. If we want to get a good observational test of our models, having an event that happens rarely in the history of the universe isn't as much fun. Anyway, all right. Well, thanks, Jonathan. Thanks, Jose. And thanks to folks on the live stream. And see you all another time.